Right, so this is A2 chemistry, 4.3 alcohols. So the first half of this is quite nice and easy. It's the stuff that we did last year in AS. So first off, thinking about primary, secondary and tertiary alcohols. So it's based on where the hydroxy, which is the OH group, is, functional group. So then just thinking a little bit about the basics from last year. Alcohols, primary alcohols go to aldehydes. Potassium dichromate is the oxidating agent and you distill it. And then aldehydes, then if you reflux it, or you can just go from primary alcohol and reflux it, the same oxidizing agent will make you a carboxylic acid. Secondary alcohols then can be oxidized using potassium dichromate into ketones. Okay, just thinking a little bit, ketone will have the C double bond, the O double bond in the middle. Aldehydes will have it on the end, so that's how you tell the difference. Carboxylic acids is obviously OH and O double bond. It's always on the end carbon again. This is the conditions for these two. Secondary alcohols will only make ketones. That's just a bit of a basic getting you started. You can also form alcohols, or the formation of alcohols can come from halogen alkanes. So alkane, just a carbon, hydrogen, hydrocarbon with a halogen added to it. So this is just a chlorine one. You could have bromine or iodine. This is a nucleophilic substitution. So you're substituting the halogen for an OH group or hydroxy group. So what happens is dipole induced here because it can sense the pull, the larger pull here. So you've got positive and negative. All the electrons are forced over to here. The OH then bonds on there. You end up with an alcohol plus a Cl. This normally comes from water, so you normally end up with HCl as well. Okay, for example, a primary methanol is produced. We reflux it, sorry, it doesn't come from water, it comes from sodium hydroxide, so you could get salt, sodium chloride. Reflux is the conditions, and that's what you need to get the OH. You can also form alcohols by doing the reverse. So instead of, so obviously we've just chatted about how you can go from aldehydes to ketones. You can also go the other way and reverse it. So the reduction of an aldehyde or a ketone, we use something called BaBH4 dissolved in water with methanol. This is a reducing agent, okay? Provides the H plus to reduce it, okay? Because obviously aldehydes are O double bond, alcohols are OH. Okay, carboxylic acids need a stronger reagent. Okay, lithium instead of sodium. Okay, borohydrate, aluminium hydrate. Okay, this is a nucleophilic addition, so you're adding something across the double bond. I've changed this a little bit because it was using a Br. So, got your hydrogen, which comes from your borate, hydrogen borate. Again, same kind of thing, a positive and a negative, forcing all the electrons up there. So that becomes positive, attracted to something that's negative. Remember, hydrogen's not often negative. Okay. And then what you've got there is one hydrogen added on there. Okay. And then another hydrogen, because this has now got extra electrons, the hydrogen then adds on. So you've got your OH group. Okay, it's not 2 bromo because I removed a H. I made it a alcohol. Okay, so that's kind of the basics. Alcohols react quite readily, okay, because they've got their OH functional group, okay, useful in organic synthesis. One way is to make hydrogen halides, okay, nucleophilic substitution. Reaction with hydrogen halides to produce halogen alkane, so an alkane with a halogen on the end. This is due to the high polarity of the H halide bond results in halides being to act as a nucleophile. Okay, so that's it reacting with hydrochloric acid. You need a zinc catalyst, okay, and you make a halogen alkane and water. Okay, exactly the same thing there with hydrogen bromide and then with lithium. Just notice, you might want to pause the screen to look, is there's different conditions. So this one is just a zinc chloride catalyst. This one you need concentrated sulfuric acid. And then this one you need concentrated phosphoric acid, and then you need some sulfuric acid as well. Okay, so you need to know the different conditions depending on what halide you're adding. Okay, another reaction then, carboxylic acid, something we did last year. So carboxylic acids can react with alcohols in the presence of a strong catalyst, normally sulfuric acid. And then you reflux it. Once completed, distilled to convert to an ester. So reflux is when it's taken, when it's going. Okay, it's the OH from the carboxylic acid to the H from the alcohol, bond together, make an ester. You sometimes have to add sodium hydrocarbonate to remove the acid so it doesn't stay too acidic, because it might not always completely turn into ester, so you might have some alcohol and some acid left over. So you need the sodium hydrogen carbonate to remove the acid and the anhydrous calcium chloride to remove the alcohol, because esters don't always fully form, and esters are good solvents. They're used to make nail polish. They're quite sweet smelling. Another thing then, okay, is to make an acyl chloride. These are derived from carboxylic acid, so they kind of look like a carboxylic acid, but instead of having an OH group, it's been replaced with a chlorine atom. Okay, very polar, react violently with alcohols to produce esters. So another way to produce esters, same kind of thing, okay, same kind of thing happening. There's your OH, there's your C, double bond O, and then there's the chlorine as well, okay. Nucleophilic addition, elimination reactions. So it's a little bit complicated what you've got going on. This O here is attracted to this C here again, creates this kind of like induced dipole with the oxygen becoming negative. That then creates like an intermediate product where you've got one positive oxygen and one negative oxygen. This oxygen then gives its electrons back here to create another double bond, and then to allow this bond to happen here, the carbon here shoves off any extra electrons and the chlorine gets left on its own. The chlorine then, wandering on its own, got 2 electrons, free electrons. It then takes the hydrogen, because this hydrogen still got this positive, oxygen still got this positive bond, takes the hydrogen, and then you end up with this. Okay, this is an ethyl chloride plus acid. Okay, and then just a little bit looking at phenol. Okay, so phenol is an aromatic alcohol, so it's got a benzene ring with an OH group, pH between 5 to 6, so it's weakly acidic. When phenol loses an hydrogen atom, the lone pair on oxygen overlaps with a delocalized electron system here in the middle, and it spreads, stabilizing it. Okay, doesn't react with NaCO3, so no carbon dioxide is produced, so it's a very weak acid. Okay, its CO bond is shorter than you'd find in an alcohol. Okay. Testing for phenol then, okay, you need to use ferric chloride, and it should turn a purple colour. Okay, if phenol is present, a vivid violet purple colour will happen in the addition of ferric chloride. Okay, and then there's 2 kind of reactions you need to know about. Reactions with halogens. Okay, so again, a dipole is induced. It's electrophilic substitution. Polarization, so it's attracted to this delocalized electron system. 2, 4 and 6 are more activated. Okay, so they're more likely, doesn't mean it will, but they're more likely to happen, and then you create an aromatic halogen alkyl. You should find a white precipitate forming, so it's another test for phenol. Okay, you can also add a nitrate ion this way. And then finally, reacting with ethyl chloride, exactly the same mechanism as before, but instead of just having carbons, we've got our benzene ring. Okay, due to the stability of the benzene ring, phenol does not react readily with ethyl chloride, since the lone pair of electrons on the oxygen are overlapping with the electron system, making it less available, so it's not as easy as the alcohol. Okay, nucleophilic addition, elimination reaction to make an aromatic ester. Okay, you sometimes have to use pyridine C5H5N, which it speeds up. Okay, same kind of thing, and we've made an ester here, and the hydrogen chloride again.